It gives me a very great pleasure to introduce you to Professor Lloyd Peck from the British Antarctic Survey, who recently gave the Royal Institution Christmas lectures, and it really is a very big honour for us to have him here tonight, talking about life in Antarctic extremes. Thank you, Lloyd.
Thank you. Okay, tonight's talk is about life in Antarctic extremes. I'm going to start off with the first part of the talk to try and explain some of the mechanisms that humans use to survive in that environment and what the problems are living in that continent. And then I'm going to move on to the animal life in Antarctica and explain how animals deal with the problems too. And then I'm going to finish off with a little bit about what the prospects are for animal life in Antarctica. So, first off, life in Antarctic extremes. I'm Lloyd Peck. I work for the British Antarctic Survey. I've been to Antarctica 10 times. I'm a marine biologist, and I'm interested in animals and environments, and there's nowhere better on Earth to work on those questions. So, Antarctica. There are some things that everybody knows about Antarctica, that we all know about Antarctica, but there are some things that fewer people know. Antarctica is a continent about twice the size of Australia. It's about 1.5 times the size of Europe. It's the coldest place on Earth. Temperatures recorded down to -89 degrees. But it's also the world's highest, driest, and windiest continent on the planet. At Cape Denison, they have average wind speeds throughout the year of over 50 miles an hour. They have in excess of 15 storms a year with winds over 100 miles an hour. It's very windy in places. The reason it has these attributes is predominantly because Antarctica is covered in a large ice sheet. It has 2 ice sheets, one on the east of the continent, this one, and the West Antarctic ice sheet, this one. The East Antarctic ice sheet is bigger than Europe, and it contains 30 quadrillion tons of ice. Yes, it doesn't mean a lot to me either. 30 quadrillion tons is a lot of ice. What you can say is the ice on that side of the Antarctic is on an area bigger than Europe, and it's 2 miles thick everywhere. The average is 2 miles thick. So that's the same as an ice cap stretching from here to Moscow and from the north of Norway down to the bottom of Spain, 2 miles thick everywhere. It contains 3/4 of the world's fresh water. So if you add up all the water on Earth, in the Great Lakes, the rivers, glaciers on mountains, in the Arctic, then there's 3 times to 4 times as much water in Antarctica than everywhere else put together, which is why people are worried in case it melts, because it would have a big effect on the Earth. It's also the world's most isolated continent. It's further away on average from other continents than anywhere else on Earth. And it's not only isolated because of the distance, it's surrounded by an ocean, the Southern Ocean, which accounts for about 5% of the world's oceans by area and about 8% by volume, that circulates round and round and round, and it's cold. It's about 2 degrees at its warmest, and these oceans, the Atlantic and the Pacific, are 5 degrees warmer at those points. So there's a sharp discontinuity in temperature, and that isolates the continent from warming currents to the north. So millions of years ago, Antarctica wasn't cold because a huge Pacific current brought heat down past the borders of Antarctica like our Gulf Stream does, and it was warmer. There's none of that now because the Southern Ocean stops it. So what's it like in Antarctica? I believe we've got somebody who's been and spent 3 years there in Antarctica. It's cold, isn't it?
Yes.
Yes, it's cold. Okay. Most of our field parties work in places like this. These are guys living in tents. They can spend up to 2 or 3 months living in tents out in a field party. These are geologists. They're going to work on these mountains. These tents are an ice cap that is already more than twice the height of Ben Nevis. The ice that the tents are pitched on is already at about 3,000 metres altitude. The mountains poking through are another 1,500 metres up. These are very high, so the altitude poses a problem. It's pretty. You get the southern lights. It's nice being in a tent when you can look at it from outside and feel very cosy and warm and homely. It's not so good when the wind blows. When the wind blows, there are extra problems. It takes away your heat. You can't move around. You can't see very far because there's lots of snow and blowing snow in the air. When it gets like this, there's not a lot you can do. Do you remember that? Yeah, it's really, really difficult. You can't go more than 4 or 5 meters from your tent because you'd get lost. So you have to be very careful. People spend a lot of time like this in a tent. I know people who spent 21 days living in a space that size because they couldn't get out of the tent because the wind was blowing constantly at storm force levels. The tent is big enough to lie down in both directions, but no more. You have to get on pretty well with the person who's in the tent with you. You read a lot, you play chess, you listen to your iPods now, but I guess in your day, you had a lot of conversations about things that were fairly inane. So, the first problem is the low temperature. And the questions are, how do we lose heat? Well, the first way that we can lose heat is through conduction. And conduction is the transfer of energy along the material. And I'd quite like to show you how this works with some volunteers. I've got some volunteers at the back who are going to come down and help me with this. 3 at the back as well, please. Yes. Now I need 5 or 6 people. Good. Okay. The energy, the temperature that a material has is dictated by the energy that its molecules have. And all molecules that make up materials are moving around. They're bouncing around with their own kinetic energy. Okay? So, I want you to be molecules in my material. And I want you to be a solid. And a solid has its molecules all very, very close together. Okay? So, you have to be very close together. Personal space is not an important criterion in this demonstration. Okay? Closer still. Come on, really close. You're tight. Okay. Now, these are molecules in a material like a metal or a very dense solid. If we start to warm it up, the molecule in the middle starts to move around because it gains more energy. So it moves about. Okay? And it transfers some of its energy to the other molecules. If I heat it up a lot and it moves around a lot, then it transfers more and more energy. And if it becomes frenetic with its movements, lots of energy is transferred to the other molecules in the material. That's how heat is transferred. If we now have our molecules in a gas, they all have gaps between themselves. And if our central molecule in the middle gets a little bit of energy and moves around, play some music, we can have a... Okay. There we are, you see. Now, the more energy she gets, the harder it is for her to pass her energy on to the other molecules. Thanks. Thank you very much. Okay, so it's easier to transfer energy through materials where the molecules are close together than further apart. That's how a lot of the insulation that we have for our clothing works. You make discontinuities between different types of materials so the molecules don't bump into each other very much, and you put gas layers, air layers, in the insulation. So, the second way we lose heat is by convection. And convection works by us heating up air and the air moving higher off us, taking heat away as it goes up. That can lead to wind chill. And we've got a video clip to show you how wind chill works. Technical problem number 2. He's up there.
Antarctica has the lowest temperatures on the planet, but something happens down here that makes the cold much worse.
In Antarctica, your body is much, much warmer than the air around you. So conduction transfers heat from your body to the air, warming it up. But air is also a really good insulator. So when you've warmed up a thin layer of air around your body, you stop losing heat so fast. But when the wind blows, it takes away that warm layer of air and replaces it with more cold air, and you have to warm it up all over again. And when the wind blows constantly, you're constantly warming up more and more cold air, and your body gets very, very cold. This is the wind chill factor.
We now have to switch back to the presentation that I'm giving. Good. And... okay. So we've seen that we can lose heat through conduction, convection. Actually, we need to go to evaporation. The third way we can lose heat is through evaporation. And the demonstration here is in your gloves and bags. So if you can take your glove out and put the glove on one hand, please. Evaporation works by a liquid evaporating off a surface. And each molecule of that liquid takes a small amount of energy with it when it evaporates. So if you take that gloved hand and you wave it around in the air and feel how that feels, concentrate on how that feels, okay? Hello, good. Now if you take the baby wipe out of your bag and wipe it on the back of the other hand, okay? Now the back of the hand without the glove, the back of the naked hand, okay? Now wave both hands around in the air, okay? You should feel a big difference between the two hands, yeah? And what's happening here is the glove is stopping evaporation from one hand, so it's stopping you losing heat from one hand, but the other hand is losing heat through evaporation, and you're losing a lot of heat. So we want to stop that in Antarctica. You want to avoid that because Antarctica is the driest continent, okay? The highest, driest, windiest continent. Wind's a problem, evaporation is a problem. So, how does polar clothing work? It has to work against all of those problems, okay? And to show you that, I've got a demonstration. And I've got some help from a person here who's going to come and show you how polar clothing works. Here's my volunteer. My volunteer is wearing our standard issue clothing for working at minus 25 degrees. This gear allows you to survive and work at minus 25 degrees. Is this a man or a woman? Okay. First off, she's got insulated hood over goggles. It's a she, I gave it away. She's got bare paw mitts, which are the same as your RAB jackets, the best RAB jackets you can get, the best down jackets you can get. And underneath those, there are thermal insulated gloves. Okay? Now we'll let her take the head over off. There's a head over, which again is thermally insulated head over. And underneath the head over, she's got some goggles. Whoa. There we go. I think she's quite keen to get that off, aren't you? Yeah. Okay. Goggles, protecting the eyes all the way down to the nose. They can come off too. Now, you can take the first layer off if you want to. Note the difficulty it is to get the gear on and off. This is an over the top. It's windproof, but it's not waterproof. Okay? And the reason that it can be windproof and not waterproof is when the temperature is that low, there's very little water in the air. It's very, very dry, so you don't get wet. Even though you're surrounded by snow and ice, you don't get wet. The next layer is a really good quality fleece jacket. Okay, layer 2. Layer 2 can come off. And underneath layer 2, we've got some salopettes, which are, again, windproof working salopettes. But before she can take those off, we need to take the boots off. Think you managed the other one on your own? Yeah. Okay. These boots are not just insulated boots. They have a thermal lining which has an aluminium fibre woven into it to reflect the heat back onto your feet. So it's a double layer boot with a thermal layer and an aluminium layer in it. Salopettes are next. Da, da, da. No, okay. Layer 4, lots of layers, trapping air, materials that have discontinuities between the molecules. It's the same in the UK when it gets cold. You want to wear lots of layers because lots of layers give you extra insulation. We've now got a thermal shirt. She was very warm inside this lot. Thermal shirt can come off. Layer 4. See, she can do it on her own now.
Yeah.
It's much less difficult. And underneath this, we've got thermal salopettes. Layer 5. You warm?
Very.
Thermal socks underneath the boots.
Sorry.
Thermal salopettes can come off now. And layer 6, which you might recognise actually, because these haven't changed very much at all. I don't know what you're doing, but that wasn't in the talk. Okay, standard thermals that you would buy and use, low alpine thermals that you would buy and use anywhere if you're going out on mountains. These haven't changed. I'm not going to ask her to go any further because it might be slightly embarrassing. Thank you very much. She is very warm. So for minus 25, there are 7 layers. Most of them are thermal layers themselves. There are windproof, and there are also one waterproof layer. But the waterproof isn't as important as the thermal layers that she'd got on. So the next question is, how can you work with all that gear on? Well, you saw that it's very difficult to move around and do things, but I've got a demonstration of how we can do that. And for that, I need a volunteer. I need a volunteer. Have I got a volunteer, please? Yes, anyone? Anyone up there will do. Come on, we'll have one of you. Good man. Okay. You've been out working in Antarctica all day, and you're really hungry, and you've got your gloves on. I'm not going to put all the rest on. You can just do with the gloves. Okay? As we said, these are standard down insulated gloves. Everything you cook with and eat is cooked on a stove like this, and all the chocolate is in a box like this. So you've got to open the box to get your chocolate out. And it's minus 25, so off you go. Open the box, get your chocolate, get your food out before you can start cooking. It's going to take you about 40 minutes to boil some water because it's so cold and you've got to melt ice first. And it's not easy, is it?
I was never good with knots anyway.
Okay. Give everybody an example. Here's a pound. If you can pick it up with the gloves on, it's yours. Yes, it's not very easy. Oh, well done. Well done.
As a curator, I have to look at historic objects with glass on.
Okay.
Maybe, but I'm not.
He's not so good with knots. No, that's fine. Thank you very much. If you're working as a pair out on an ice cap, and you're working with me and I fall into a crevasse and break a leg, you've got to fill a hypodermic syringe with morphine and inject me with it. And if it's minus 20 and you're wearing all that gear, you have the choice of taking the gear off, possibly getting problems from the cold yourself, or muddling your way through while I'm screaming blue murder with a broken leg. It's not an easy thing to do. It's why we're very careful. It's why people get trained a lot. It's why they get first aid and they get extra training in how to deal with casualties compared to most first aid work. It's not easy to do, but it's worth it. So what happens if the gear doesn't work? Well, first problem could be hypothermia. And we should have a video clip of hypothermia to show you the characteristics of the problems of hypothermia. Yes.
The water in this tank is held at a constant 12 degrees centigrade. That might not sound very cold, but it could kill me in a matter of hours. And I'm going to try and sit in this tank for 60 minutes. To check my vital signs during the experiment, I'm wired up with electrodes. The most important being a rectal probe. This will measure the temperature deep inside my body, my core temperature, which is usually 37 degrees centigrade.
I'm feeling a little bit tense, a little bit nervous. Don't know quite what to expect, except for I'm going to go into that water bath over there and I know it's going to be cold. I've been cold before, I just don't know how cold this is going to get.
In 5, 4, 3, 2, 1. Now, just pop your feet in.
I might not be showing it, but this water is very, very cold. A real shock to the system.
First couple of minutes are the worst. The reason we've got Lloyd in the water is because you cool very much more quickly in water than you do in air. So it means we can demonstrate all the things that happen to the body with cooling in a shorter period of time. You cool about 3 or 4 times faster in water than you do in air at the same temperature.
This is bloody cold.
Now, experiencing what it's like to rescue when hypothermia.
It's odd, but once you've settled, you know it's cold, you know your body's cold, but it doesn't feel really, really unpleasant, it just feels a bit unpleasant, whereas when the temperature changes and you're going in, you really do notice that.
Well, Lloyd's half an hour into his immersion now, and his deep body temperature has fallen by just about 0.5 of a degree, or half a degree. He's doing really well. The shivering starts very lightly and intermittently and gradually becomes more and more continuous and more intense. And we're just slipping into that phase now. And all the time, of course, his hands and his nerves, but now his deep organs are starting to cool. So gradually and gradually, the cold incapacitates you, moves towards paralysing you. And he's now half an hour, 3/4 an hour on the way towards that happening.
Come on! Control. I don't just feel cold.
OK, we're going to go through one more set of tests, Lloyd.
My ability to do even the most simple tasks has been severely impaired. Compared to before the experiment, my grip strength has roughly halved after 50 minutes in the tank, and my manual dexterity has become almost non-existent.
So now we can see that Lloyd's hands are like claws. You know, it's really difficult now to oppose finger and thumb and to move the fingers independently. So it's a really difficult task at this stage. If you're trying to undo something or trying to tear something apart, he's lost grip strength and he's lost manual dexterity. Very, very important for survival actions in a cold environment.
Before the experiment, this test took only 19 seconds. Now it takes over 3 times as long.
Done. 70 seconds. OK, that's it. That's the 1 hour up. We're going to slowly now get you up, move you over into the warm water.
After 1 hour, I'm a shivering wreck. With my loss of strength and manual dexterity, I am rapidly approaching the point where I would not be able to rescue myself. All because my core temperature has dropped just 1 degree.
And going straight down.
But fortunately, I don't have to endure any more cold. Now I get to recover in a nice warm bath.
Well, that felt cold when the feet first went in. Then it felt really hot.
Now, we saw your rectal temperature in this experiment fall from 37.05 down to 35.7. Now, if that had continued to fall at around about 33 degrees Celsius, you'd have just got slower and slower and then slipped into unconsciousness. Around about 30, you can start to get spontaneous problems with your heart, and death normally intervenes at around about 25 degrees Celsius. Now, there's a big variation.
But some people have survived much lower temperatures.
Okay, so all the problems that you saw that I had there were only with a temperature drop in the core of 1 degree. People are very intolerant of temperature drops in their bodies. If you have a 10-degree drop in temperature, of your core, it's got a good chance of killing you. So that's a real big problem. So what are the problems are there, as well as hypothermia? Well, there's frostbite. Frostbite looks like this. This person has got a severe problem, fingers and toes, of frostbite. The next stage after that is everything rots. In the first slide, the fingers and toes were dead. Here they've rotted. I know one guy had a case like this and he cut his fingers off with a hacksaw because he couldn't feel nothing with the fingers. Clamped the fingers in a vice, cut them off so that he wasn't carrying them around because he couldn't afford the doctor's fees in America to have the operation. He then pared the extra tissue down with a Stanley knife and stopped when he could start feeling things because paring off dead tissue has no effect. What about the animals? We have warm-blooded animals that live in Antarctica. We can wear 7 or 8 layers of thermal insulation to solve this problem. They don't have the technology. Well, what about penguins? Penguins use feathers. Most bird feathers look like this. We're all familiar with what bird feathers look like. This is a penguin feather. This feather is a standard penguin feather. It's off a chin-strap penguin. And penguin feathers are short and spade-like. And at the back, they have a little piece of duvet jacket. Okay, a little piece of down at the back of the feather. They also have more feathers per square inch than other birds. They have 72 feathers per square inch. And the spade-like shape of them means that when they go in the water and the feathers are pressed together, they form a waterproof outer casing. So they're wearing a little duvet jacket underneath a really impressive waterproof. And that's done naturally. But it did take them something like 100 million years of evolution to solve the problem. But even that's not enough for some penguins. These are emperor penguins. They survive the winter in Antarctica at temperatures below -50. And even the feathers they've got and the insulation they've got don't work well enough there. They have to huddle. And by huddling, they keep each other warm. They take turns on the outside, and they can survive temperatures 3 times as low as your freezer at home. Okay? 3 times lower than your freezer at home, these penguins live in every year. Seals don't have feathers. So how do seals cope with these problems? Seals have fat. And we should have another video clip to tell you about fat in the world's fattest seals. Here we go.
You know, some of the fattest creatures on Earth live in the coldest seas on the planet around Antarctica. One of these is the world's biggest seal, the elephant seal.
These guys are absolutely massive. Bulls like this one weigh in at over 3.5 tons. They're built like this not just for insulation, but because they need to fight. The bigger they are, the better they are at fighting. And the better they are at fighting, the bigger of harem of females they can defend.
Okay, so elephant seals, male elephant seals are really big. 3.5 tons. It's about 4 to 5 times as big as the biggest cow that you've ever seen. They are really huge animals. The males are this big to fight. They're about 40% fat. But interestingly, the females, like this one on the left, are fatter than the males. Male on the right, female on the left. She doesn't say no very often. The females are fatter. They're about 45% fat compared to the males at about 40% fat because they suckle the pups. They give a pup in a month about 3/4 of their fat. The pup triples in weight, from about 20 kilos to over 60 kilos in a month. And that's all from the female's fat reserves. So when she comes ashore, she's really fat. She wants to mate, she wants to give birth and suckle the pup because she's got a large amount of fat that she needs to lose. Great diet. Absolutely great diet. But the shape of the animals is important too. If you think of lots of animals that live in warm areas, things like orangutans, monkeys, things like giraffes, they have long, large appendages. Animals living in Antarctica, warm-blooded animals living in Antarctica, have a round shape with relatively small appendages. Whales around, penguins around, seals around. So shape's important. So shape, insulation, and the way you live is important for all these warm-blooded animals to survive those extremes. But what about cold-blooded animals? Well, living in these mountain tops, temperatures in the air go down to -70 in the wintertime, and they go below -40 in the protected rock habitats, where the proper Antarctic animals live. The animals that spend their whole lives in Antarctica, reproduce and stay there all the time. And these are those animals. This guy's looking at them. These are some of the commonest animals in Antarctica. These are mites. There are 3 species of mite there. They're very similar to the mites that live in our beds. Everybody's got them in their beds. They eat the skin that sloughs off our bodies while we're asleep at night. These animals scrape lichens, algae off the rock surfaces to live, and the little orange ones are predators, so they go around eating the other mites. The biggest animals in Antarctica are these guys. These guys go up to 38 feet long and eat scientists in the winter months. These are springtails. The biggest one is nearly 2 millimetres long. Most of them are about 1.5 millimetres. And like the mites, they live on algae and lichens. They can survive these low temperatures because they've got a whole battery of antifreezes, antifreeze proteins, they've got glycerols, glycols, sorbitols, a whole range of chemicals that allow them to survive very low temperatures. Some of them get rid of water so that they can make the salt concentrations in their body stronger to avoid freezing, and some of them can supercool. And you all think water freezes at 0 degrees, but it doesn't freeze at 0 degrees. If you take out all of the impurities from water, all the bacteria, all the dust, all the large molecules, take out all the particles that ice can grow on, you can get water down to -40 before it freezes. In my lab, we regularly take our lab water, our lab distilled water, ultra-pure water, down to about -5, and it doesn't freeze at -5. So water only freezes at 0 normally because there's lots of things for the ice to grow on. And when there's lots of things there, it always freezes at 0. But that's called supercooling. And some animals remove those ice nucleators from their bodies. They can lower their freezing points by about 8 degrees. By doing that, they can do that in a matter of a couple of hours. I'm a marine biologist, so I've got to talk about marine biology. This is what the marine environment looks like in the summer at one of our stations. This is what it's like in the winter, and it is different. The sea has frozen, there's lots more snow and ice. Antarctica in the summertime looks like the picture on the left, and there's very little ice around the margins. Well, actually, this piece of ice is bigger than the UK, so it is a large piece of ice, but it's relatively little. In the wintertime, it looks like this from a satellite, and 15 million square kilometres of sea ice are formed. Again, it's a number that means very little to me. However, it's twice the area of Australia. It doubles the size of Antarctica. It's about 1.8 times the size of Europe. An area of ice like that freezes round Antarctica every winter. In the summertime, my group and I can work diving from boats. We can dive from the seashore, and we can work on the animal communities we want. In the wintertime, when the sea's frozen, you can't dive that way. So you take out your 5-foot chainsaw and you cut a hole through the ice. You then tie ropes on to the divers, because it's clearly important that the diver can find the hole again at the end of the dive. However, I've been on 2 dives where we got to the far end of the dive, signalled that we were going to come back, and pulled the rope in because the guy hadn't tied it off properly at the far end. First time wasn't too bad because we went out with a slope on the right, we came back with a slope on the left till we could see the hole, and then we came out. Second time we'd gone across a flat piece of seabed and we didn't know which way was back. Fortunately, after sitting and thinking for about 3 or 4 minutes, and I was panicking a little bit, my partner realised that divers blow bubbles and that there's ice on the surface and you can see the bubbles on the ice underneath. So we went up and followed the trail back to the hole, and I climbed out and proceeded to try and kill the person who was on the end of our rope. So yes, it's very important, and now every diver's roped, so both divers in the pair are roped. We have through water communication systems, so those problems don't occur anymore. Underneath, you can see where the hole's been cut and the ice blocks have been pushed out the way. Seals cut their own holes in the ice to breathe in the wintertime. There are 3 or 4 species of seal that spend the wintertime in Antarctica. These are crab eaters. So when you cut a hole, they kind of think that's pretty good because they get a free hole to breathe from, and they often decide that they want to share your hole with you. And sometimes you just have to push them out of the way to get out. The scenery is spectacular. Ice cliffs and icebergs underwater are some of the most amazing phenomena that you can see. Ice that's been deep in a glacier before it goes into the sea is compacted, and all of the air is pushed out of it, and it's like glass. And you cannot see where the ice starts and the water ends. And you can put your hand out and it stops in water, and you cannot see where it stops and starts. It looks like the ice starts a foot or 2 further on from your hand. Your hand just stops in the water. It is a surreal experience. These are the most difficult conditions. You can't use ropes because all this broken ice moves around and you get tugged around. And it also moves around and bounces around on the seabed. So if you're working on the seabed and doing some work and a piece of ice bounces around on top of you and it's the size of a house, it's pretty serious stuff. So these are our most strenuous diving conditions. So what's the environment like? Well, these are the most variable and the least variable temperatures in Antarctic Ocean. Sydney Island has the most variable sea temperature in Antarctica. In the winter, temperatures hover at about minus 1.8. Come the springtime, they shoot up to a summer maximum of about 0.5 degree. Sea temperature, the most variable in Antarctica, is about 2.5 degrees throughout the year. In McMurdo, where it's most variable, it goes from about minus 1.9 to about minus 1.7 throughout the year. It's been like that for millions of years. Animals living in that sea have lived with temperature variations of 2 degrees or less for 10 to 15 millions of years. Long time for evolution to adapt them. There are not many animals on the land, but in the sea, it is very diverse. Very, very diverse. There's a great array of animals living in the seas in Antarctica. For some groups, sea spiders, amphipods, sea cucumbers, there are more species on average than for the average for the planet. So, 17% of the world's sea spider species live in the Southern Ocean around Antarctica, on a seabed that accounts for about 5% of the world's seabeds. So they're 3 times as diverse as the average for the planet. There are lots of different types of species and lots of life in the Southern Ocean. What are the characteristics of these animals? Well, they grow very slowly. These guys are brachiopods. For the paleontologists in the audience, this is time to wake up. These are brachiopods, which are the commonest fossils on the planet. These guys live to be 55 to 60 years old. Brachiopods in Europe live to be about 10. These guys don't start reproducing till they're 20 years old. They grow very slowly. They live a long time. They don't reproduce very often. Development. Well, you can look at development in different types of animals by looking at their development stages. This is a baby sea urchin. It's about 200 microns long. It's about 1/5 of a millimetre long. When the sea urchin gets to that stage, you can say how long it takes to get to that stage, and it's a very accurate measure of how quickly they develop. This is a baby polychaete worm. This is going to grow up into, well, if we hadn't killed it and preserved it and put it in an electron microscope, it would have grown up into a fan worm living on the seabed. This is a baby ribbon worm. And this is a baby snail. In fact, if you look closely, you can see it's got an operculum that closes off the shell, and here's the shell, and here's its foot. So by getting to these stages, we know how quickly they develop. If we look at the snail development, in Antarctica it takes about 200 hours to reach this stage. Everywhere else on Earth, it takes between 5 hours and about 80 hours. Development is a lot slower, ×2 to ×10 slower. They develop slowly, they grow slowly, they live a long time. These are the metabolic rates of bivalve mollusks, things like mussels and oysters living in Antarctica. Low metabolic rates compared to the temperate zones and the tropical zones. Something like 5 times slower than a typical temperate mollusk. So they do everything really slowly. The low temperature has some strange characteristics too. This is an ice fish. And the cold means its metabolic rate is very low. But also, the oxygen content of water goes up as the water gets colder. There's twice as much oxygen in seawater in Antarctica as in the tropics. And that means this fish doesn't need hemoglobin. It has no red blood cells. It has no hemoglobin. It has no globins in its body. It has no myoglobin in its muscles. It has no molecules for carrying oxygen around its body. It provides oxygen to its tissues purely by oxygen dissolved in the fluids in its body. So you cut this fish and its blood runs clear. You cut its muscles and its muscles look translucent grey and white. There's no red muscle. There's no pink coloration. The gills are white. Its heart is white. Its muscles are white. Its blood is clear. And it can only do that because the water is very cold. If the water warms up at all, 2-3 degrees, this strategy is not possible. So, this is a common question I get asked by people when I come and give a talk. Is size everything? Well, most people in the audience think that size is quite important, but they don't think of size in the same way that I think of size. In Antarctica, we have some animals that are very similar to animals that we all know and that we all have in our gardens. So, in our gardens, we've got these guys. These are woodlice. This is a woodlouse. Woodlice are members of a group of animals called isopods. Okay, this one came out of my garden this morning. He's going to go back in my garden tonight. Okay, it's an isopod. It's a very common group of animals. There are isopods all over the earth. And in the oceans around the UK, isopods grow up to about the size of my thumb. Well, in Antarctica, we have isopods. This is an Antarctic isopod. It's a thing called the giant Antarctic isopod, Glyptonotus. This is about half the maximum size they get to, half the length. They get up to about this big. Okay? There are no crabs and lobsters in Antarctica. Don't run away. It's all right. It's dead. No, it is dead. These guys take the place of many of the crabs and lobsters. They're one of the big scavenging groups. The Antarctic isopods get up to about 50 times the size, the weight of the biggest European isopods. But there's an even better example. This is a sea spider. And I was told if I stood still long enough, the close-up camera up there would try and get a picture of this sea spider. Here we go. Are we watching? Oh, closing in, closing in. Okay. This is one of the biggest European sea spiders. Nearly. It is very small, isn't it? The biggest European sea spiders get up to about 5-8 millimeters across. Okay, so here's one. This one came from Millport. Okay. If you're a decent marine biologist, you'll be able to go around the coast of the UK on a big low tide, look in the rock pools, and you'll be able to find these. They're pretty cryptic, they're pretty hard to see, but they're there all the way around the coast of the UK, all the way around Europe. Okay, sea spider. Related to terrestrial spiders, related to scorpions, sea spider. But this is a sea spider. Okay, this is about half the size of the biggest sea spiders in Antarctica. It's an Antarctic sea spider. Okay, are they edible? Are they edible? Well, they are for some of their predators, yes. These animals have very small bodies, very large legs, okay? And because of that, they have many of their organs in their legs. So they have their guts and their gonads in their legs, very much like Chelsea supporters. Sorry, do we have any Chelsea supporters in this? Okay, so we have very large size in some groups in Antarctica. This is an example of two groups, the isopods and the sea spiders. So the isopods get up to about 1,000 times heavier than the biggest sea spiders in temperate latitudes. The sea spiders are huge. The isopods get up to huge size. These are amphipods. Amphipods are the group of animals that you commonly know as sandhoppers. So if you walk around the beaches at high tide, especially at night time, you'll feel things bouncing off your legs. Those are sandhoppers. Those animals are amphipods. The amphipods in Antarctica get up to nearly 10 centimetres long. They get up to about 4 inches long. You don't want to have those bouncing off your legs while you're walking around on the beach. That's one of the Antarctic amphipods. This is an Antarctic sea gooseberry. They're called sea gooseberries because in most parts of the planet they look like gooseberries. And this isn't even one of the really big ones. I don't want to give you the impression that everything is big in Antarctica, because most amphipods, most sea spiders and most isopods are small. But there is the ability to get large, and some species get really large. Evolution pushes animals out into the scope of their envelopes that they can live in. Large size is a possibility in the Southern Ocean that isn't possible in other oceans around the planet. So some groups get very, very big. Why do they get big? Well, it's the oxygen story again. If the temperature's low, your metabolic rate is low. Your use of oxygen is low. Because there's more oxygen in the water, you can supply more tissues with oxygen. And that's why you can supply more tissue with a given amount of oxygen, you can get bigger. So what's going to happen if the climate changes? Well, I would hope that you'd be able to put together some of the story that I'm giving you so far. The fish with no blood pigments, if that warms up, he's got a big problem. My group's been working on climate change on terrestrial animals and marine animals. Terrestrial animals survive huge changes in temperature during a day. When the sun's out, temperatures where they live can go up to +20. At night time, it can go down to -35, -40. They are not going to have a problem coping with a warming environment. Their problem is from animals coming in from outside, from South America, from Australia, and just out-competing them. So the terrestrial biologists are worried about alien invasions. ET comes to Antarctica, and that's a real problem. The marine animals, the problem is survival. And the problem's even bigger than I told you already. These animals are clams. Note how fast the temperature, the time code is going. It's 8 o'clock, 8:15, 8:30, 8:45, 9 o'clock. These animals are burying in the sediment. These clams, they're like, anybody eat clam chowder? Anybody? You've eaten something that looks a bit like this. It's a relative of these animals. These clams live buried in the sediment. If an iceberg takes them out of the sediment, they have to rebury or they're going to die. So it's a critical activity. And we've been looking at critical activity. The population can rebury when you take them out of the sediment. You find that by the time you get up to 4 or 5 degrees, none of them can rebury.
At 0, nearly all of them can rebury. At +2, only about half the population can rebury. And the half that can't are the big animals, the reproductive animals. So for the population, 2 degrees is a real problem because all your big animals have an inability to carry out critical biological behaviours. It's the same with limpets. If you take a limpet off a rock and turn it over, at 2 degrees, half the population can't turn back over. They're in big trouble. So these are indicators of a loss of ability to do some critical function. And 2 to 3 degrees looks like the time where many of the populations we've looked at have problems. This is the part of the Antarctica where the British Antarctic Survey did most of their work, on the Antarctic Peninsula, off on the South Orkney Islands. This is the main Antarctic continent, and this is South America. It's also the region of possibly the fastest climate change on Earth. Air temperatures on average have gone up between 2 and 3 degrees in the last 50 years, and sea temperatures here have gone up by 1 degree in the last 50 years, which is a lot more than the average for the planet. There are only 2 other places on Earth, and they're both in the Arctic, where temperatures have warmed anywhere near as much as this over the last 50 years. So on the peninsula in Antarctica, some of the fastest climate change anywhere is going on. It's interesting, but down on the main continent, there's been very little change. So in the East Antarctic, with that big ice cap, temperatures have changed very, very little. An immeasurable amount over the last 50 years. But here, where we're working, it's a big change. This is a plot from the Hadley Centre climate model. It's one of the best that's around at the moment, and it's predicting that in the next 100 years, sea temperatures are going to go up by about 2 degrees on average for the planet. Air temperatures are going to go up by about 4 degrees on average for the planet. Of course, like everything, it isn't going to be the same everywhere. The yellows are the largest change in temperature, the reds are the next, the pinks are the next, and the whites show very little change. So the big areas for change are in the subarctic, the subantarctic, the Arctic and the Antarctic. And some areas are being predicted more than a 6-degree rise in temperature over the next 100 years. They're in the polar regions. That will have significant consequences for everybody, especially the animals that live there. So the first thing you can do if the environment changes is you can cope with what you've got. And I hope you'd agree with me that looking at the physiology of the animals that I've just shown you, they haven't got a big capacity to cope. The next thing you can do is evolve. Your ability to evolve depends on how often and how many offspring you can put into the next generation, the statistical number of chances you've got for a mutation. That depends on lots of things. Antarctic animals like this fish, well, this fish lives to be about 35 years old. It starts to reproduce at 9 or 10 years old. Similar ecology fish in the UK and in temperate zones start reproducing at about age 2, some at age 3. So there's 3 times to 4 times as long before they start reproducing. These animals produce about half as many eggs as typical temperate fish of the same size, and that's partly because it's colder. Their eggs are bigger. Animals in low temperatures produce bigger eggs because the development time is longer. So they produce less eggs. They don't start reproducing until they're older. They have less statistical shots at evolution than similar animals in warmer temperatures. The brachiopods too, they live 5 to 10 times as long. They don't start reproducing until they're 20, instead of temperate brachiopods that start reproducing at about age 3. So they don't evolve as fast. Your third shot is migrate. And you can see this happening around the world now. Animals are migrating as the climate warms. So the idea is that along the continental margins for marine animals, things can migrate to colder water. And some studies are starting to show that this is possibly happening already. There are big problems where you've got big rivers like the Amazon, because there's 140 kilometres of sediments here. So any animal living on a rocky shore to the north who wants to get colder has a bigger problem than animals in most places. What are the prospects for a marine animal living around Antarctica if it warms up and it wants to move south to colder conditions? Well, there's a problem, because there isn't any water further south. And because of the shape of the continent and the fact that it sits over the pole, it means marine animals have a bigger problem moving to colder water than almost any animals anywhere. The ocean circulates round and round and is approximately the same temperature everywhere. So on all three major criteria, Antarctic marine animals seem to be more at threat than anywhere else. And some scientists are looking at them as kind of a canary, because they're likely to be one of the first big groups to suffer losses through climate change warming. The planet's complex. It's changing. We're almost certainly having a big effect on that. Antarctica is one of the last true places where man has had little effect in the past, and we're starting to affect it now. Let's hope we're not seeing the sun going down on some of the world's most rare and exotic animals on the planet. Thank you for listening.
Thank you very much, Lloyd. Now, we do have time for a couple of quick questions if anybody has a burning issue they'd like to raise.
I was just wondering what was happening in terms of trying to save these species. Is there some kind of artificial environment being provided to save certain members of the species at least?
The answer to the question is no. Where we have conservation measures on most continents on Earth, the conservation measures that are being taken in Antarctica are purely for people to leave the environment alone, to designate areas where tourists can't go, to designate areas where the scientists don't take samples, where nobody's allowed to go and do any more than identify what the organisms are that are living there. So we do have, if you like, the equivalent of marine parks. The idea that you could run an aquarium system sub-zero for some indefinite period in the future and maintain long-term populations of some of the most threatened species there is kind of a bit daunting for most people to even think about. The London Aquarium were thinking about having an Antarctic exhibit 3 years ago and gave up just because it was too complicated a system to run. So I think it will be the last place where the save a species conservation types are taken up. Also, people aren't going to be as interested in trying to save a sea spider as they are from an eagle living in California, are they? Yeah. Or some primate that's got nice eyes and fur and looks vaguely human, and therefore the anthropomorphic issues all come into it.
Good evening, sir. When we were down there was a lot of krill feeding, of course, seals and the killer whales, etc. I wonder what your views on the krill population and so on would be as time goes on, whether this would still be you know, in its millions, or whether these would slowly disappear as well.
There's been a lot of work on krill over the last 20 to 30 years, and krill populations in Antarctica have declined since 1980 by about two-thirds. About two-thirds of the krill have gone since 1980. The wintering of krill is carried out on the undersides of sea ice, and the predictions are that sea ice is going to decline progressively over the next 50 to 100 years.
and it means there'll be more of a problem for krill populations to survive. Nobody's quite got a handle on whether they think it's going to become critical for the survival of species that depend on krill, but of the 17 species of penguins, something like 13 of them have krill as their major food source. There are 5 or 6 of the great whales that depend on krill as a major food source. Several species of seal do. So there is a worry that the krill populations are getting down to levels where they are going to impact on some of the kind of furrier animals with big eyes that people care about. So that is an issue that's currently getting a lot of effort going into it. I think krill will decline. I think it will affect the survival of at least the species of 2 penguins within the next 50 years. But that's my opinion.
Do we have time?
The anemic fish and the enlarged spiders, are these evolutionary changes or physiological adaptations?
They've definitely occurred through evolutionary processes because they are species characteristics. So you have a species that is very large. Within that species, you do get variations in size and variations in characteristics of the fish, and those are the physiological or the adaptations within the species. So if you like, the answer to your question is actually both, because the biggest of the biggest sea spiders are produced by an evolutionary process producing a big species, and then the biggest of those are produced by the physiological adaptation within the species. And it's the same for the fish. Those Antarctic ice fish vary in their characteristics. They vary in the size of the heart, their circulation rates. They're not very active. They tend to just sit and wait until food arrives, and then they'll eat it and sit still for the next 5 hours while they try to get their breath back after moving. But the characteristics of the individuals are produced by adaptations through development and throughout their lifestyle.
Thank you very much, Lloyd, for a fascinating talk, and may I wish you all a very safe trip home. Thank you.